Good afternoon from the UK. Thanks for joining us today for this webinar. My name is Ben Knappett. I'm product manager for the Sunny Suite LNP synthesis instruments. I'm joined today by Alex Kerr, one of our senior application scientists. How's it going, Alex?
Very well, Ben. Thank you.
Great. So Alex is going to talk to us today about making light work of liposomal synthesis and development using the Sunshine instrument. So before we get into the slides, if anyone would like to ask a question as we go along, there is a Q&A button in the Zoom toolbar that you can click either at the top or the bottom of your screen. And if you would be willing to submit your question without clicking the anonymous button, that will allow us to get back to you by email after the fact in case we run out of time. Otherwise, we won't know who the question's from to get back to you. Okay, without further ado, I'm excited to hand over to Alex and we can get right into it.
Thanks a lot, Ben. And yeah, welcome to my presentation on making light work of liposomal development and optimization with Sunshine. It's a pleasure to be talking to you today, and thanks a lot for coming on. So without further ado, since COVID and the advent of the lipid nanoparticle vaccines, there's really been an explosion of interest in the nanoparticle-mediated drug delivery across the pharmaceutical sector, with investment and attention pouring in. However, this has been almost exclusively focused on the delivery of nucleic acids by LNPs with cationic or ionizable lipids. But lipid-based nanotherapeutics have a much greater span than the delivery of just nucleic acids. One of the first liposomal products to hit the market, Doxil, has been around since at least 1997, so it's seen it all. And with a global market for liposomes of around 8 billion in 2025, 15 products on the market and many more in clinical trials, they're not going away anytime soon. So they remain a much bigger market than lipid nanoparticles. And I have to say, I was pretty pleased when we started getting more requests in for application support from some of our customers for liposomal formulations, as they're a really interesting and versatile drug delivery vehicle that I haven't worked with for years. And these nanoparticles can take just as much benefit from the modern advancements in nanoparticle production and analysis as LNPs can. So to catch anyone up if they're not familiar, the key component of liposomes are phospholipids, and these are similar to those that make up our cell membranes. They have a hydrophilic head and hydrophobic fatty acid tails, and there are scores of variations on these lipids, from saturated tails like the DSPC pictured here, commonly used in both LNP and liposomal formulations, to unsaturated lipids. There's naturally derived lipids such as egg sphingomyelins, to fully synthetic manufactured lipids. And these can all have different tails, linkers, head groups, charge, and more. And this allows for huge variation in the materials and behaviors of the final nanoparticle. In an aqueous environment, the lipids line up to protect the hydrophobic tails, with the hydrophilic heads on the outside, as you can see here, forming a lipid bilayer. And then when there's enough lipids, when the raft is big enough, it's energetically favorable for the bilayer to wrap around and form a sphere, so those hydrophobic tails are completely enclosed and protected from the aqueous environment. And there you have a liposome, which is a lipid bilayer or multiple bilayers surrounding an aqueous core. And the hollow spherical structure of a liposome is one of its key advantages compared to other nano delivery vehicles. So in this internal reservoir, hydrophilic pharmaceutical actives can be entrapped. Worth noting that hydrophobic actives can also be trapped in the bilayer, which has been done in some of the products on the market, meaning that liposomes are also just super versatile regardless of what kind of active you're working with. And this entrapment brings several benefits from a drug delivery standpoint. Firstly, bioavailability. Poorly soluble drugs that have to be given in small doses to avoid rapid excretion from the body can be entrapped in a longer circulating or more biocompatible liposome, allowing for better uptake of the drug. Secondly, controlled release. The release of a toxic drug can be extended so more can be dosed at once without reaching harmful levels in the patient's bloodstream. And thirdly, targeted effects. Liposomes are often targeted at tumors or specific parts of the body, whether through passive targeting, such as the enhanced permeation and retention effect in tumors, so EPR, where the particles are small enough to slip into the leaky vasculature that tends to surround tumors to release their payload locally, or through active targeting measures, such as adding antibody fragments to the external liposome surface. And what are people optimizing when they're screening liposomal formulations? Well, as with any complex nanomedicine, there's a lot to deal with. Two examples pictured here are changing lipid composition to adjust the permeability of the membrane. So long saturated lipids like DSPC tend to pack very tightly, causing the membrane to have low permeability and high rigidity, and therefore a really slower drug release. Other additives such as cholesterol can help with this too. On the other hand, shorter or less tightly packed unsaturated lipids, represented here, will create a leakier bilayer, less densely packed one, which will lead to faster drug release. So you can tailor that by tailoring your lipid composition. Lipids can also be selected for their fusogenicity, or ability to interact with target cell membranes. So improving this, which is largely down to the shape of the lipids that you use, can help your lipid membrane fuse with a target membrane, and due to the curvature, cause the bilayers to fuse and help you release your drug cargo straight into the cytoplasm of the target cell. Other lipid compositions may be chosen to affect the way the body and immune system react to the nanoparticle, the physical properties of it, the biodistribution, or things like improving the loading and encapsulation efficiencies during the process of making the liposomes. So there's loads of things to be thinking about with a formulation optimization program. And with all of this in mind, how do people tend to make liposomes? So the classic and most common way is called thin film hydration. In this method, lipids are typically dissolved in a solvent, most commonly a methanol chloroform blend, which is obviously a lovely combination. And the solvent is then removed by rotary evaporator to leave a lipid film on the vessel surface. This lipid film is then hydrated using your buffer of choice, so often PBS or a similar neutral buffer, typically resulting in a pretty polydispersed suspension of a mix of unilamellar, so single bilayer particles, and multilamellar or multi-layered liposomes of all different sizes. Following this with techniques such as high pressure homogenization, sonication, or extrusion, where the material is heated and repeatedly passed through a nanoscale polycarbonate filter, are used to reduce the particle size and lamellarity to give the small unilamellar vesicles, or SUVs, that are typically the desired morphology with liposomal formulations. There are exceptions to that rule. And so what would this look like if you're screening multiple liposomal formulations and particle characteristics? Well, it would look something like this, which makes me feel a lot like this. That's a lot of processes for each sample, a lot of mess, a lot of waste, all of that, and it's still not suitable for lots of sensitive actives or lipid materials due to the high pressures and temperatures present in the extrusion or high pressure homogenization processes. So really not ideal for a modern high throughput screening approach to formulation development and optimization. So what's the solution? Microfluidics has a whole host of benefits. How does it work? In the case of liposomes, the lipids can be dissolved in ethanol or pretty much any other water-miscible solvent if necessary. This lipid solution can then be mixed with the hydration buffer using super accurate pumps and precision constructed microfluidic channels, so the mixing is perfectly controlled and reproducible. As the organic lipid solution mixes into the aqueous phase, the medium polarity causes the bilayer rafts to form that we were talking about earlier. These then grow, and eventually, when the medium becomes polar enough, they will close to form your final liposomes. The speed of the mixing process, as well as the solvent and formulation materials, of course, allows exact selection of particle size, and the excellent fluidic control means the particle size distribution is both reproducible and very narrow, which is obviously excellent for pharmaceutical products. It also tends to make small unilamellar vesicles, those SUVs, in a single step without the need for additional steps or harsh processes after formulation. Hydrophobic additives can be added into the organic phase, and hydrophilic additives can be added into the aqueous phase, or more commonly, added after in a process called remote loading, but that's a bit beyond the scope of today's seminar. And all of this at ambient, gentle conditions in a single step. So lots of benefits there. Are we done? Not quite. There's still a lot of testing to be done. You're still looking at testing a lot of materials and solvents and mixing rates, and these will all have an effect on the particles. If we're doing this one by one, either with disposable microfluidics or a system that needs, say, manual washing or resetting up between samples, we're still dealing with a potentially clunky, slow, and wasteful workflow. So we've made some improvement, but really for rapid throughput optimization for your workflows, this still leaves a bad taste in my mouth, and we think we can do better. So what is our solution for liposomal synthesis? Here is Sunshine. It combines cutting-edge microfluidics with the power of automation. You just load your two phases into the sample loops in the bottom of the system here. The system then uses driving fluids to push your samples through the flow path. And this means a few things. It means minimal dead volume because the flow path is swept through with driver fluid. You can fractionate samples in the loop, meaning you can run multiple discrete conditions and automatically collect different experimental conditions within a single experimental setup. And finally, it's also self-cleaning. So the driving fluid is used to thoroughly clean the system between samples. Also worth noting, the microfluidic mixing chip, or Sunny, can be used again and again too. It's made of super high quality etched glass, which is really unique in the world of microfluidics in terms of its chemical resilience, its rounded channel shape, really unique that, and its surface smoothness, which is just plus minus 5 nanometers. And this is compared to closer to plus minus 1 micron in injection molded chip technologies. So that's orders of magnitude more surface roughness in those. Sample sizes are from 1 mil up to fully continuous flow. And it's designed to transfer straight through into our GMP instrumentation, the Sunbather, when you're happy with your process. And what does this look like in action in a development process? Here we have Sunshine running two complementary experiments on liposomal formulation. One is looking at the effect of changing the flow rate ratio, which is your ratio of aqueous to organic phase. You can see we're running from 2:1 to 10:1. And the other is changing the total flow rate, or TFR. And these both have implications for the particle size and distribution. And this is what a sample slug looks like when it's passing through a microfluidic Sunny. We've used fluorescein in input 1 there, and a blacklight to help visualize this. You see the Sunny is clear before an experiment. The samples are then released from the sample loop, so they meet on the Sunny at the same time. And the exact timing will depend on your flow rate ratios and total flow rates, as well as your tubing volume. All of that, though, is programmed into the software for you, so you don't have to worry about it. The sample packet is then flushed through the Sunny by the driving fluid, and it's really possible to see how effective this is for propelling the sample through the system and cleaning the microfluidic channels here, as the fluorescent slug transits the Sunny and goes dark again almost immediately. That sample would then be collected by our fully automated collector with the user's choice of sample size, head and tail waste cuts, and collection vessel. So the system is set up to use either 2 mil, 8 mil, or 15 mil collection vessels, depending on your needs. A cleaning cycle is then carried out both between each experiment in a set of experiments, and at the end of the experiment, a more extensive cleaning cycle is run. And then we're ready to add our ingredients for the next experiment. So quick, clean, and easy. And so this is what you see with the standard DPPC cholesterol-based liposome. We used a molar ratio of 55 to 45 respectively in ethanol, and used PBS as the aqueous phase. You can see as we increase the flow rate ratio, we're increasing the aqueous phase ratio compared to the organic flow rate, compared to the organic phase. And this means the solvent polarity increases more rapidly, leading to faster mixing with less chance for those lipid rafts that form to grow and aggregate before it becomes favorable for them to form a sphere and a liposome. This therefore leads to smaller particles. So we're seeing what we expect to see here. More rapid increase in polarity for the liposomes, smaller particle formation. Of course, the higher the flow rate ratio, the less lipids of a certain concentration are present in the same unit volume. So the process can become slightly less efficient. So you're always looking at balancing different inputs in your final process. We then did a screen of total flow rates between 4 and 12 mil per minute. This is all at a 5:1 flow rate ratio. It seemed like a good medium of good PDI and particle size, but reasonable productivity as well. And this again, you see a rapid initial drop in particle size and PDI, polydispersity, which then evens out. We did this in 2 separate experiments, but given they both use the same material, actually all the conditions used here could have been combined into a single experimental run, which I think is really exciting. And that is simple, rapid, and fuss-free optimization of liposomal formulations. Those 2 brief experiments gave us 7 experimental data points, with no need to clean in between experiments, no expensive consumables, and a total runtime for all the samples of just 15 minutes. Plus, whilst they're running, you can crack on with preparing your downstream workflow, get the next set of formulations ready, or start analyzing your data from the last run. Now that's more like it. We can screen with style and confidence. And actually, it was so easy that I decided to do some more. We compared 4 phospholipids here, all had phosphocholine head groups, but there was 3 different hydrophobic chain lengths, so 18, DSPC, 16 and 14, DPPC and DMPC. And then one with the C18 tail with a double bond as well. And we ran those at 3 different flow rates, 4, 8 and 12 mil a minute again. And with Sunshine's automation, it was really a breeze to run these 4 experimental setups to rapidly screen and collect the 12 1 mil samples. And interestingly, straight away, you can see that DPPC and DMPC level out in size at 8 mil per minute, but DSPC and DOPC are still dropping. From our early experiments, we can see that perhaps if we wanted to drop the particle sizes of the central 2 liposomal formulations here, we could look at changing the flow rate ratio, or of course, other things like changing the solvent buffer and mixer type to get smaller particles. And we've graphed the effect of chain length against particle size for the liposomes produced at 12 mil per minute here. And there seems to be a really clear relationship between the carbon number and the particle diameter, which is really interesting. The longer chains actually produce smaller particles at these conditions, and unsaturation leads to even smaller particles than that. So that was a nice little tidbit of data, and all of this data was collected in much less than a day. It took about half a day or less to run and measure all these formulations. So this is an illustration of just how rapidly Sunshine lets you build a picture of your formulation space. It's really unique in that regard. So now we have an idea of how these formulations behave. We tried loading the liposomes with a marker dye to assess how effective passive loading of a hydrophilic active would be using this setup. So we loaded the aqueous phase with 1 milligram per mil of brilliant blue dye, and then dialyzed the resulting liposomes for 24 hours to get rid of the free unencapsulated dye, leaving just the loaded liposomes behind. And it's really worth mentioning here another string to our high throughput formulation screening bow, which is Stunner. Stunner is a single instrument that can provide information on size, distribution, and concentration of particles, along with quantification of the payload, whether that's a nucleic acid or some other molecule. And Stunner is the only instrument that pulls together UV-vis concentration, rotating angle dynamic light scattering, or RADLs, and multi-angle light scattering on the same 2 microliter sample. So you just load 2 microliters of sample into a Stunner plate. You don't need to bother with sample prep or dilution, as the microfluidic plates allow for coverage of a wide dynamic range if you're dealing with a full plate. You get 96 concentration measurements in 10 minutes. You add on your rotational angle DLS sizing from 7 different angles, which is really industry leading, and have it all done in around 2 hours. So for even heavier workflows, you can hook it up to your favorite robot to add even more oomph. And here we can see exactly what sample loading looks like, again using some fluorescein and a black light. So in 2 wells, we've already added our 2 microliters of fluorescein. And as you can see, to load another sample, you simply add your 2 microliters into that input well, and the sample wicks into the plate through capillary action. So it's super simple and quick with a minimum of prep, and it's compatible with multi-channel pipettes too for those really high throughput screening days. And a really interesting thing about Stunner as well is that you can train it on your specific analyte to get the most accurate data. So you just load a dilution series, and Stunner can automatically generate the absorbance spectrum, the maxima, the extinction coefficient. And most importantly, it can separate out different materials using the unmix algorithm. So in this case, there's just a little bit of turbidity and noise from the lipid components, which are blue in the model that was built up by Stunner here. But the system is so accurate that it can be used to separate protein signals from nucleic acids if you're looking at functionalized lipid nanoparticles. So it's really, really a cool piece of kit. So after producing the dye-loaded liposomes, they were dialyzed against PBS to remove ethanol and unencapsulated dye, as we mentioned earlier. And Stunner could then be used to read both particle size. Because we're using RADLs, we can get both Z average particle size and mass mean diameter particle size. And we can get the encapsulated dye concentration. And so here, combining the rapid sample production of Sunshine and the high throughput size and payload analysis of Stunner, it was really a piece of cake to make these 3 dye-loaded liposomal samples of different sizes and rapidly analyze the loading level of the dye and the encapsulation efficiency. Passively loading liposomes like this is quick and easy, but it tends to have a relatively low encapsulation efficiency. In this case, we got 15 to 20% across the flow rates tested, with no significant trends identified due to the change in total flow rate. And it's interesting that this figure is still well above the relative volume of the liposomes compared to the bulk medium, suggesting that perhaps the dye also has a pretty high affinity for the liposomal bilayer, which is entrapping a lot of the dye. Again, just really rapid access to really interesting data from these bits of kit. And so you can use Sunshine and Stunner to deliver your optimized liposomal payload on time and on target every time. Thank you, and I hope you enjoyed this presentation. I could really speak for much longer on liposomal formulations, the addition of other components such as pegylated liposomes, which is possible, bilayer curvature, and all of these really, really interesting things. But I think we've got to draw the line somewhere, and it seems like a good a time as any. So I'd be really interested to see if there's any questions for me to answer or any comments. So yeah, let's get a discussion going. Thank you very much.
Great. Thanks so much for that, Alex. That's all fantastic information. So we have a bunch of questions coming in, which I'll start to go through, but please do feel free to keep adding them. If we do run out of time, we will be following up afterwards to respond to those by email. So we will get you an answer to any questions asked. Cool. Okay, so to kick off, there's a question here asking about what the maximum volume of liposomes is that Sunshine can produce. So I guess what's the range overall that we can work with?
Sure, yeah. So Sunshine actually has 2 modes. It's got protocol mode, where you're looking at running these small fractionated samples, and those range from 1 mil up to about 6 or 7 mil, depending on your flow rate ratio for an individual protocol moded experiment. And then we've got continuous mode, where you bypass all of that and using the sample loops. And in that mode, you can run as much as you want. Essentially, you can run fully continuously for as long as you need to produce the amount of material that you need. So it's super versatile. You can take your 1 mil of protocol mode sample, decide you want to make 100 mil of it or even more, and just run the exact same protocol through sunscreen, just using continuous mode instead of protocol mode. So yeah, super versatile in terms of the sample volumes involved.
Fantastic. All right, and then we have another question here asking about GMP compatibility and is it suitable for manufacturing?
Sure. So Sunshine itself isn't designed to be suitable for a GMP environment. It's got features like inline pressure sensors, which make it quite difficult with those electronics to make it GMP compatible. How it is designed is that the pump architecture, the mixing chips, and the system overall is designed to be exactly like our GMP solution device, which is called Sunbather. So the idea is that it will be very easy to run in continuous mode with your Sunshine to do your method development, and then port that across to a Sunbather placed in a GMP environment without any further changes to the methodology. So you can just be really confident that your segue from preclinical material production through to fully GMP material production is super easy and hassle-free, and you don't have to spend loads of money getting your CDMO to optimize a formulation when you can do it in-house and just port the method across wholesale.
Thank you. Perfect. Another question asking how many times you can reuse the microfluidic chips and whether there are any other consumables involved in making your liposomes.
You can use the glass microfluidic chip a lot of times. Really, there's nothing to stop you continually reusing it. We do recommend swapping it out after maybe 3 to 6 months, depending on the level of usage and the kind of materials you're using, but that's really up to you to define how foul do you think it is. As we say, the glass surface is super smooth, so it's really easy to clean. Because it's so resilient, you can use pretty harsh cleaning solvents. If you take it offline, you can fill it with something like chloroform to really clean out any lipid deposits and stuff like that. In terms of other consumables, there's nothing on an experiment to experiment basis, apart from maybe the syringes you use to inject your samples into the sample loop. So the running costs compared to something that uses disposable precision microfluidic chips is super low.
Perfect. Thank you. Another question here. So how are you may have answered this in the presentation, how are the liposomes characterized to know what you think you have in terms of size, mixture of liposomes, uni versus multi-lamella, etc. So obviously we've talked a bit about stunner, but I guess the difference between something that maybe is singular and multi-lamella is an interesting question.
Yeah, that's an interesting one. So using stunner, you can't really tell the lamellarity of the particle. DLS is just measuring the size of the particle as it travels through its solvent environment. And honestly, I'm not sure what technology could identify how lamellar a particle is, apart from maybe TEM or something similar, cryo-TEM, so you can actually physically see the particles inside. I guess the other one might be an X-ray based technology. So you might see different scattering from something with a lamellar structure. But really, when you're running liposomes in formulations like this using microfluidics, you're much more likely to get SUVs than you are to get MLVs, just because of how the particles are forming.
Great. Thanks. So, all right, someone's asked here what your lipid concentration was for the experiments you were running in the ethanol.
Yeah, fair question. In this case, they were all 10 milligram per mil. Kept that steady. But you know, we've worked with higher concentrations than that, 20 milligram per mil or even higher, and you can work with much lower concentrations if you're looking to conserve material as well. I think the lowest we've run with is sort of 1 to 3 milligram per mil of particle forming material in the organic phase.
Yeah, sounds good. And when particle size seems to decrease as the flow rate increases, we have somebody asking whether you think that has anything to do with pressure drop or any other thoughts on what contributes to that.
Yeah, so Potentially, but I would imagine that it's largely to do with the speed of mixing at or just after the junction. So effectively, the mixing is going to be more efficient. The faster that it happens is going to happen faster when the materials are running faster. That mixing process is going to be more violent. I say violent, we're still well within the lamellar regime, so the pressure drops aren't really that high. Most of these particles do seem to have some kind of size limit formation where the size of the particle stops being defined by the speed of the mixing and plateaus, as it's instead defined by how fast the lipid rafts can aggregate, which I think is pretty interesting. It's pretty hard to separate out pressure drop from the other factors that are going on there. But you can do things like measure. There was too much data. In 2 days, I produced way more data than it was possible to include in a single webinar, unfortunately. But I did do an experiment comparing the DOPC formulation using a 190X chip. So that's got an 190 micron junction, and a 275X chip, which has a 275 micron junction. So at the same flow rate, those two are going to have very different pressure drops. So the 275, the larger junction chip, had a pressure drop that was still way below 2 bar, whereas the 190X was probably slightly above 2 bar. And actually, once you start hitting the beginning of that plateau, the pressure drop isn't making a difference. So yeah, it's potentially, it has an effect, but I don't know whether that's realistically able to be separated from the effect of just speed of mixing due to the speed of the materials and the channel geometry.
Okay, and we are just over the half-hour mark, but I think we have time for one more question. So we have you are aware of any evidence from literature about liposome modifications in order to promote their delivery to the brain? Is that anything that you've seen any information about of late?
Yes, absolutely. There was, well, it wasn't liposomal. There was an LMP paper recently about using peptide conjugation to help pass through the blood-brain barrier. I've seen more information actually about solid lipid nanoparticles and their ability to potentially cross the blood-brain barrier. So that's an interesting one. And there is polymer-based technologies, which also seem like they've got really good capabilities for passing through that barrier as well. So there's a few potential options there. And I guess it's the race is on to see which ones are going to make it to the clinic first.
Absolutely. Okay, well, I think that's all we have time for today. I just want to say thank you very much again to everybody for joining us on today's webinar. Thank you to Alex for the wonderful presentation. And if you do have any other questions come to mind, do feel free to reach out to us. You can do so on our website at www.unchainedlabs.com. And for those of you who asked questions we can get around to, we will get back to you by email. So thank you very much for submitting those, and we'll get in touch with you soon. Thank you very much, everybody, and have a wonderful rest of your day wherever you are. Bye-bye.